a very good, it is a noon, so a very good noon to everyone. Respected sir, uh, all the participant, respected madam, and all the member who are organizing this workshop. So the next session, Sir J.P.Singh, he- sir is an HOD. Sir is an HOD in the Department of Computer Science and Engineering and IT Patna. And sir is a he has completed his PhD from the University of Calcutta. Even sir has he is among the one who author in many textbook like the C programming, data structure, OS, ad hoc network, and sir also has many reputed publication, journal, and conference. And mainly, sir is focused on his research interests are mainly consists of deep learning, and social media mining, and social network and information security. So we have invited sir to talk about the linear regression and the linear discriminant function. So, sir, I welcome you, and please carry on the talk, sir.
So thank you, Amika. Thank you for your
Yes.
introduction. And uh, now, as Amika told that here I'm going to mainly deal with the basic, what is how to go ahead in the machine learning technique. And I think this is just the second session. I'm sorry I was not present in the first session, so I do not have enough idea about what was talked. But I will start from very basic, and I will ask the participants to interrupt me, interact with me whenever they feel that some extra, say some sort of communication or some sort of more explanation is needed, because that will make this talk more interesting and in fact useful. Otherwise it will be just one way talk, and classroom I will like to get questions and in between, so don't think that sir will be interrupted as why I should ask this question. So if something is coming in your mind, please ask at that particular time. So now I am moving on to my slide. I think my slides are visible to you.
Yes, sir. Sir, it is visible. Yes, sir. Yes. Yes.
So today I will talk about mainly two topics: the linear regression and the logistic regression. That's two topics I will concentrate, and I just want to give enough background so that the rest of the topic can be easily built on. So we all know, I think, in the first half, or in fact, all of us, those who are present, I presume that everyone knows what is supervised learning. So supervised learning is a technique where we give right answers while we are training the system, and the system trains on that. And regression is basically where we have continuous valued output. So like if we want to predict the house prices, there we use regression. And whenever we have like this is one case of regression, you can see that given a scenario, if we writing facility is not there, okay. So given certain, say if we assume that we want to predict the house prices in some locality, and we have seen that from previous records that if the house prices are directly related to the size, the overall size of the house in terms of feet. So if I say some data we have collected is something like this, that if we have 2104 feet house, then the price is around 460 lakhs. If this is 1416, the price is 232 lakhs, and so on. So if we have collected some data, and now we want to predict that given a new house is being listed, or you are trying to sold your house, or you are trying to buy a new house. In that case, you want to get an idea in this locality what amount will be sufficient to buy a house in this area. So given an unknown data, now we want to find out, or we want to predict that what can be the price, or what can be tentative price. In this sort of data, we say that m is the number of training samples. So we'll have rows, number of rows will be, say if there are m number of rows, those m will denote the number of training sample. This is x. So this x is the input variables or features. Here in my example, I have taken just one input variable, but in reality, there will be a number of input variables ranging from one to, sometimes it may go up to hundreds, thousands also in some cases, depending on the cases. Like if we have say bioinformatics cases, then this number of features may go up to thousands also, more than thousands also in some cases. Y is the output variables. Here we have one target variable, but in some cases, what we call it as multi-class and so on, classification, and we can have more than one output also. But for the timing, we are assuming that, okay, if we have just one input and one output, so one feature, this input is also called our independent variable. In literature, in mathematics, this is called as independent variable. We prefer to call it as features. So this is our feature. So size in feet is our feature, and price in rupees lakhs is the dependent variable, or the target variable, or the output variable. So we normally call it as target variable. And one pair of x and y denotes the one training example. And in general, by x, y in ordered set represents our training cases. And this is what ML workflow looks like. So what we have is, what is in our hand is, we have a training set. So we collected some data from the existing scenario. So we surveyed, or we had already existing system. We went to a broker, and then we found out from his diary that size of the house and at what price he sold. And then that will consist of a training set for us. Then we will develop a learning algorithm, which will based on certain hypothesis. And once a new house is given, now if the size is given, size of a new house is given, we can estimate the price. So we have a training set which is already there, and in supervised, that means we have both the features as well as the target variables. Then we will select a learning algorithm, and for every learning algorithm, we need to tune certain parameters, or we basically create an hypothesis. Hypothesis is nothing here, but it represents tuning. Like if you have an experience of tuning that old FM radio or TVs, you know how to tune that knob. So there used to be a knob, and then say 92.7, and then you start tuning it. Sometimes it crosses 92.7, it becomes 92.8 or 92.75, and then there used to be a noise. Then you just backtrack, or say just rotate in other direction, and then again you come down, and then you try to rotate in another direction. So that's the scenario we are going to do, and that's what a machine learning algorithm is going to do. So that sort of tuning it is going to do with the help of, so these learning algorithms will have certain parameters, and every learning algorithm will have a different sort of knobs and different number of knobs. So now if I give an analogy, so that's the analogy. I hope that analogy is clear to you, that we have a learning algorithm. So that learning algorithm will have certain number of knobs or certain number of tunable parameters which we can tune, and tuning those parameters also, if we how to tune those parameters, obviously this tuning will be based on this training set. So because we do not know the rest of the world, so we only know this training set. So based on this training set, we tune that parameter. Once this parameter is tuned, basically we say that the learning is over, and now my system is ready for predicting some new things. Then we give a new house, say new size of a new house, and based on those tuned parameter, it can give us an estimated price of that particular house. Now there are some questions we need to be answered. Now what is this hypothesis? So what is this H? And how to represent this H? So that's the main issue. So as I told that these are my tunable parameters. So how to represent? So in what fashion these tunable parameters will be connected with each other? And how to represent this? So basically, how, if they are connected in some fashion, obviously they has to be connected. So once they are connected, how this can be represented? So like one example is shown here, like that in the first case, if you have seen that, say this is my house, say size of the house in feet, and say this is the prices, then we can plot that data something like this. And we want to fit, or we want to find out a curve, we want to find out something which will fit this. So in linear regression, basically we are trying to find out a line which will fit this. So there can be several lines. Like if we go, I'm sorry, I'm using a PDF and it is very difficult to say draw something on that. So I will be frequently moving on to this. So we have something like this. Sorry, this. So we had certain parameters or certain things like this. So this is what the scenario was. Then we can fit a line like this. We can fit a line like this. We can fit a line like this, or we can have something like this. This represents and this is a straight line. So we are trying to fit with this data a straight line. So if we are fitting a straight line to this data, obviously this will be a linear regression. So we call it as a linear regression. So there can be a number of lines. And if you now assume that tuning of that example, that analogy I told. So if it is a straight line, what are the parameters? So for a straight line, we know straight lines are represented as y equals to mx plus c. This is how we represent a straight line. In our case, we are representing that, okay, my h can be represented as, my hypothesis can be represented at, say, let this c is written as theta 0, and then we have a theta 1 x. Why I am coming to this theta? Because in rest of the article I have used theta. So this is a straight line, that's all. Instead of y equals to mx plus c, we are writing something h equals to theta 0 plus theta 1x. Now this theta 0 represents the slope. So for this line, so this will be my theta 0, sorry, this intercept, not slope, this intercept. And the slope is represented by theta 1, not directly, but in terms of this tangent function. So theta 0 and theta 1. If we have theta 0, 0, if we assume that theta 0 equals to 0, then probably we'll have a line like this. Sorry. It will pass through the center. Sorry, origin, not center, origin. It will pass through the origin. If we assume this is theta 0 equals to 1, so it will, on this axis, it will have 1 and then it will move. And similarly, if this theta 1 is say 1, then this slope will be different. If this is 2, then there will be a different slope. So basically, if it is theta 1 is 1, then it will be at 45 degree. If it is different, it will accordingly, either it will be slanted on this side or it will be slanted on that side. It will be moving on that side. So that's what a linear regression are basically, what we mean by this linear regression. And that's what we are saying in this slide. So if we have that, so we can fit a curve here. And if we try to fit a linear straight line here, then that linear straight line can be represented by h of, why we are writing this h theta x, because this is a function of x, this variable, we have just one variable x. So this is a function of x, and we have certain parameters theta which needs to be tuned. So mathematically we write it as h theta x. h theta of x is equals to theta 0 plus theta 1 x, what I just saw had represented on that paint window. So this is an example of linear regression with one variable. We also call it as univariate linear regression. Now there are two terms, one variable, so because we have just one x, and linear because these equations do not involve um, there is no exponent in these variables, so it is linear in that sense. If we would have more than say one variable, so if we have say in some cases if we have features like say if we have a feature like x1, x2, x3 and then y, we can have some data like this, say like size of the house in feet, the number of bathrooms, number of bedrooms, and then we have three different fields, and then we can write this h theta can be written as what? It will be theta 0. If we are assuming a linear regression, then it will be theta 1 x1 plus theta 2 x2 plus theta 3 x3. So this is how we can represent this. So if we have more than one variable and if it is linear, then we can represent it like this. So we can have theta 0 plus theta 1 x, says in plus theta 2 x2 plus theta 3 x3. Now as I have already told that these theta i's are the parameters, so we need to estimate. So we had two questions. First question was how to represent this x, how to find out the relation between different parameters of the x. So that is represented in a linear equation by this theta 0 plus theta 1 x. My next question is, the next important thing is how to find out this theta i's, because once these theta i's are known, then only we can do something. If these theta i's are not known, it's impossible to find out, or it is impossible to fit. Or as I told that, basically what we are trying to do is we are trying to tune this. So how to tune this, or how to find out the best values for this theta? This example is slightly different, or these cases are slightly different than that even the radio tuning or the TV tuning, because in TV and radio tuning we know where we should come to that, so what is the basically whether it's correct or not. But in this case it is very difficult to say because we do not know the exact value. So how to find out this theta is? So again, let us see an example, and then let us discuss. Say if I have x1, say let me take just one variable, so that will be easy to explain you. If we have say x and say y, and we have 1, 3, 2, 5, 3, 7, 4, 9, and 5, 11. Values are there. Now, if we try to find out a line, so we know that this can be fitted as hx can be written as theta 1 plus, sorry, theta 1, theta 0 plus theta 1 x. Now, how to find out this theta? So that's the question. So let us first start with an arbitrary value. Let us first say we assume that this theta 0 is, say, assume. So that's what we do normally. And then we try to find out how good or bad we perform. So if we assume that this theta 0 equals to 1 and say theta 1 is also 1, then we can find out, my system will predict something, say y hat which will be how much? It will be 1 plus 1. So if x is 1, so it will be 1 plus 1 into 1. So it will be 2. If say this is x is 2, then 1 plus 2. So it will be 3. It will be 5, I hope. 1 plus 3, sorry, 4. It will be 4. It will be 5. It will be 6. And now you can find out. So there is an error in every line. Let me erase this. So what is the error in every case? So E. Now we can compute the error. So what is the error? So error here can be, if we say that this is y minus y hat is my error. So say E equals to y minus y hat. Then error can be 1, 2, 3, 4, 5. Ideally what we want? We want that this error should be 0. Now, in these cases, what we can do, we can say, okay, I will add all these errors and I can try to minimize that error. This error should be as low as 0. So this error should tends to 0. That's the target. If we can do that, if this error is 0, that means my system has predicted correct for that. So this error should be as low as possible, or ideally it should be 0. Now let us say that we had say theta 1 equals to, so in this case we had theta 0 equals to, sorry, 1, and theta 1 was also 1. And in that case the error was, so if we plot my error, so this is error, sorry, I'm plotting this error for say only one value, say for theta 1. So I am plotting this for theta 1, theta 0 I am fixing, and this is my error. Am I clear so far? Hmm?
Yes,
How
sir.
much mistakes I am making by if I assume that theta 0 equals to 1 and theta 1 equals to 1, then the error what we are making is this one. Normally, if we add this error, we can get an average error. But the issue is, in some cases, this error can be positive as well as negative. Here it's a very handcrafted, very simple example. So all the errors are positive, but in some cases it might happen that the error is negative also. So normally what we do, we take square of this error. So we take square and then we calculate this error, something like this. And then we can say that, okay, this is my say squared error, because it's a squared number. So since it is squared, so there is no notion of, so these errors will not cancel out. Again, I am repeating, this error sometimes can be positive, sometimes can be negative. Don't only think of this example. In general, this error can be sometimes positive, sometimes negative. So if we simply add them, it may cancel out each other. Since this may cancel out each other, so normally what we do, we take the square of those terms and we take square as average of that squared error. So if we take average of the squared error, so what we can find out here in this case, it is 45 and 55. So the error in this case is 55. So if I say that, okay, at this is 0, 1, 2, 3, I'm trying to explain how to find out this theta. So in statistics, there are different techniques. Say this scale is of 10, 10. So this is 10, 20, 30, 40, 50, 55 here will be there, 60 and so on, 70. So at theta, and this is 1, 2, 3, 4, 5, 6, 7, 8. Let me write this in a correct way. So when theta 1, and this is only for theta 1, similar diagram can be obtained for theta 0 also. So if you think of this theta 1, at when theta 1 is considered to be 1, you can find out that this squared error is coming out to be around 55. So at this location. Okay, then you thought, okay, that's a huge error. So let me make this theta 1 as 1.5. You will come to that why I am making it 1.5. I can make it different also. So let us think that, okay, then I hello. थोड़ी देर बाद बात करेंगे. Theta 1 is, say, if I increment it, okay, increase it to 1.5, I can decrease it also, I can make it 0.5 also. So let us make at 1.5. So if I make it 1.5, this value will be 1.5. I'm sorry, I'm not calculating this. I'm sorry. So we will calculate this. These values will change. This value will become 2.5. This value will become how much? This will become 3 plus 1, 4. So let me just draw. This will become 4. Why 4? Because this was theta 1 into x. So x is now 2. So 2 into 1.5, 3 plus 1, 4. This will become 3 into 1.5, 4.51, 5.5. This will become 4 into 6, 6 plus 1, 7. And this will become 5, so 7.5, 8.5. So this is now the new value which has been predicted if we assume theta is 1.5. So if theta is here. And then you can find out this error is, so just 0.5. This error is 1 now. This error is 1.5. This error is 3. And this error is now 2.5. And you can find out the square term. So it is 0.25. It is 1. It is, I think, 225. So 0.225. Sorry, 2.25. This is 9 and this is 6.25. And if you again add this error is now 15, 17, 18, around 19 or 20 it will come. So this is here, somewhere here. So now you can see that this error has decreased from that to that. If I now make it as, say, 2, you can find out that this error will become 0. So this point will come here. So this error will become 0. If you again make it 2.5, you will find out that this error will be at 2.5, this will be somewhere here. Again at 3, this error will be somewhere, say here. So it will be something like this. I'm sorry, figure is not very good. So this error looks like this. And you have to find out this point, which is the minimum one. I hope the intuition is clear, exactly what we are trying to do. So we assume some value. So there is an analytical solution. Remember, so for whatever I have just shown you, this is a machine learning view. But if you go on through a statistics class, they already have a MLE technique, analytical solution, by which they can find out all these parameters analytically. But we are not going to do that. We are going to do, say, if we are going to do a machine learning program, or if you are trying to make your system understand, mostly we go in this fashion. So even in your neural network classes, which I think will follow in the later half of this course, you will see that the same technique is being used. So neural networks are also doing the same thing, and they are trying to reduce this error. So this error surface is for theta 1, and this error is basically a convex error surface. And if this is a convex error surface, we know we can easily use say algorithms, or we have some very good algorithms which can find out or which can converge to this local say global minima, or which can find out this point where this error is the minimum. In some cases, if it in logistic sorry in linear regression, although you will not find that, but in some cases you may also find out error surfaces which looks like this. We'll see later on. So, so how to find theta is? So idea is choose theta 0 and theta 1 so that it is close to our training examples. So for that we define a cost function, which we have already I had explained you here. So I defined a cost function. So my cost function is this difference. So this is the predicted value and this is my real value, a target value. So it's just a reverse one. I had shown here right y minus y here. All that hardly matters. You can easily understood if I would have written it y hat minus y, then also this these errors would have been negative only, but squaring it would have made the same value and this result would have been same. So there is hardly any change. So even if you write it yi minus this whole square, it will remain same. There is absolutely no difference in that. So we define a cost function and say this cost function is j of given number of parameters, so theta 0 and theta 1, and we take an average of this. So since there are m number of samples in the database, so we take that for every error. So for every sample, what is the average error? So what we do, we take the square of this difference. So the predicted value minus the real value whole square, and for this is basically an average is taken. So average means you sum up all this error and then you divide it by the number of samples. So j theta 0 theta 1 is 1 by m, I equals to 1 to m theta 0 xi minus yi. So that's my cost function. And as I had told that if we assume that okay theta 0 is 0, last case I had assumed theta 0 was 1, then this h theta x can be written as theta 1x, and this cost function will now try to minimize theta 1 only. And so if we have this case, if we have certain data samples which are there, and if we make theta 1 equals to 1, you can find out this error is 0. But if you change this theta 1 to be 2, this will be slightly above. Theta 1 equals to 0, it will be below, and so this sort of error surfaces we will get. This we have already analytically I have shown you that for different cases how this error value will change. Now if this is my error surface, I think in several courses like AI and several other courses you have already seen how to minimize this sort of error, or even in mathematical optimization courses. I'm just going to give an idea about the gradient descent, or how to really in computers machine learning techniques how we normally go. So what we do, we start with some theta 0 and theta 1 as I did here. So you might have noticed that I started with a random value. I told that okay I will start with those two knobs and I will take a random cell value, and then I will start changing this theta 0 and theta 1 till it is reducing. So if it is reducing that value, I will move into that direction so that this j theta 0 and theta 1 comes to a minimum. So this idea, this algorithm is called as a gradient descent algorithm, just opposite of hill climbing. If you remember hill climbing, so again I am repeating what is gradient descent. A gradient descent technique is you start with some initial values of those parameters, whatever parameter, whatever number of parameters you have, that hardly matters. So even if you have 10 parameters, 50 parameters, you start with some random values and then you change these parameters. So you do certain modifications in those parameters and you measure the error. So and then you do another, if this error is lesser than the earlier case, that means you are in the right track. So you move ahead into that. So you assign those new values to those parameters. Otherwise, you apply or you add some new value. Am I clear? in this idea of gradient descent?
Yes, sir.
So in general, if we write gradient descent, the equation for gradient descent can be written in general like this. So theta j, so for one parameter, basically we are doing this changes is being done for the parameter. So if you remember here, if you see here, what we are tuning this thetas. So theta 0, theta 1. So for each theta, so say for theta 0, what we are doing, theta 0 equals to theta 0 old. So theta 0 new is basically theta 0 old minus alpha. Alpha is a learning rate into partial derivative. Now the question is, so once we were here, so first time in as first value we calculated or we found that the error is here. The next value the error was here. So the question is why we should come this side? Why not we have selected some other value? Why not we had selected say 0.5? Sorry, uh, 0.5 will be here, no? It was 1.5. So why not we selected some say 10, 15 or some other value, say 0. I could have selected 0 also. So why I selected that 1.5 or say 0.5 or 2.5 and something like that. So what we can see here that this is a convex surface, and that's why I told that this error is called as a convex. So since this is a convex area, and in convex area, so it's like a bowl. So wherever if you start or if you assign a random value to these parameters, somewhere so you will fall or your error will fall somewhere in an area like this. So somewhere your error will be either you will be on this side or on this side or here or here. So based on that random initialization, your error will come onto somewhere, says either here, somewhere on this sort of surface. And then if you say that okay, where I need to go, since you are trying to move down, so that's why the name is gradient descent. So since you are descending, so you are moving towards the valley. In general, what we say that okay, if you are in a say terrain and your eyes are closed and you can only now you have to move down into that terrain. So how do you do? So you will by your feet you will try to find out which surface or which side is the lowest part. So probably that will lead us to that will lead me to valley. So that's what we try to find out, which side is lowest. So from here I can move to either this direction or this direction. Now I have to find out which direction I should move. So for that I can find out gradient. So gradient will give me this slope, and negative of that gradient will give me that okay, I am going downwards. So if I calculate positive gradient, we will be going up, what we do normally in hill climbing technique. If it is gradient descent, we take negative of that. So that's what is shown here. So negative of d by del by del theta j. So if it is theta 0, it will be del by del theta 0, and j of theta 0 theta 1. So if you just see it, so if we compute it, our j theta 0 theta 1 was basically theta 0 plus, sorry, yes, theta 1 x. Now we are trying to find out this, say, del values. So if I take del of del theta 0 of what? Sorry, j is not this. J will be this minus y. So this is what? Because my j is this one. So if you define this cost was this. So my j will be, this is my cost. So j will be 1 by m. So if I am just thinking of theta summation here, and then this whole square. So if I just think of theta 0, so it will be 1 by m, then theta 0 plus theta 1 x minus y whole square. So in fact you can take this m outside. So if I take this m outside and move this move this del by del 0 here, so I can write something like this. So and 1 by m we can keep outside because that's hardly going to change anything. Now how to take derivative? So we'll take derivative of this. If we take derivative of this, first of all there is a square, so that means it will be 2 into this whole thing. So theta 0 plus theta 1x minus y into, and then we will take derivative of this whole thing. So if we are taking derivative of this whole thing, so del of del theta 0 with respect to theta 0 will be 1 and rest will be 0. Sorry, rest will be 0 because those are say constant for this theta 0. So theta 0 doesn't depend on theta 1 or y. So it will be something like this. So it will be 2 into theta 0 plus theta 1x minus y. So if we try to minimize it, so now you can see here, that's what I have written here. So for theta 0, a gradient descent of the linear regression will be theta 0 minus alpha 1 by n, this whole thing which I had written here, this one. So this 2 in most of the cases, sometimes people take half also to cancel this out, or you can consider this 2, what we consider here as 2. So but here you can see in my slide 2 is not available, so you can assume that this 2 is already subsumed in say m, that you can easily, because these are constant number, and this is now your h. So this part, this whole part is my h and this is y. So this is what is shown here, you can see h theta xi minus y. So for theta 0, this is my equation, and for theta 1, if you do this whole thing, that the same thing for say theta 1, if you repeat this process for theta 1, so if you repeat this for theta 1, this part will be fixed, but in the next case it will be 0 and this will be x, because theta 1x, derivative of theta 1x will be x. So now this can be simplified. If it is simplified, you can write it as theta 0 plus theta 1x minus y into x. That's what is wrong, shown here, into x. And obviously this alpha and 1 by m, these are already fixed, so they are outside. So this, if it is a linear equation, so now what we can do with a linear regression model, if we think of, so given certain data along with their target variables, we will try to fit. So if it is a single variable, then equation will be theta 0 plus theta 1x, and then we can assume that okay, for theta 0 we will assume an initial value, for theta 1 we will assume an initial value, then we will find out the error, and then we will change this value of theta 0 and theta 1 using these equations, and this process will be repeated until we get a convergence. Now here is another point to consider, this alpha. Now what this alpha will do? So let me clear it out. So say if we have, I hope this up to this is okay.
Yes, sir.
Very simple thing. No? Okay, so say we have something like this, we started from here. Now what this alpha is basically doing? So this alpha is basically called as learning parameter. Now, what this learning parameter is doing? So this, why this is called as learning parameter? First of all, this is called as learning parameter because if you remember, those who are, I think all of us are student or we are student at some point of time, and still we are learning. So we are student, all of us are a student. But during exam, so if you think of that, when you want to build a concept, you go very slowly. So you read a book line by line and try to understand what is told in that, each and every line. But during exam, if you might have noticed that I have seen several students basically finish the whole book within say 10-15 minutes. And before entering that exam, so at the entrance of the exam, you almost every student almost finishes half part or sometimes the whole book, isn't it? Because so before, while we say revising, so revising means what? We take a longer step. So we do not build concepts there. We just go through and try to remember things. So similar things is represented are done by this alpha parameter. If I say the alpha is very large, so say if I say alpha is 2, that means I will take a longer step, something like this. So the gradient descent, if you see the equation we have already seen. Okay, so let me write this equation. So just, so this is my equation. So this is the equation. Not copy it. Let me write it. So the equation is theta 1 equals to theta 1 minus alpha, and say I'm skipping this 1 and something here into x. So this is what we had, and theta 0 was similarly theta 0 minus alpha and something. Now this part will be fixed for all of them because this is anyway fixed, say for one particular sample, because y is fixed and then whatever will be computed is fixed. So say this value, so for alpha 0, theta 0, if we are assuming this value will give certain number. So say this gives 2, say for example, and say alpha is also 2. So then what will happen? 2 into 2. So the old value of the theta will decrease by 4. So the steps you will be taking might be something like this. But if I make this alpha say half, then the steps you will be taking will be something like this. Am I clear? Because these values, so this thing is fixed for one sample. If this is fixed, if I am multiplying this, whatever is coming from this with some value. So if I say alpha is 2, that means the change, so from here, probably I will jump directly to this place. Or from there, I will directly jump to this place. Then I will directly jump to this place. So now if you see that from here to here, you normally come in 2 jumps only. So you are converging very fast. So this reading is similar to the reading normally student does while he is at the last phase of the examination. So just a day before examination or at the day of the examination. But if I say this alpha is half, or say alpha is even lesser than that, 1/4, then to come from this place to this place, you need 8 steps. So you are moving very slowly. So if alpha is very small, you will move very slowly. But if alpha is too big, then you will jump. So your convergence will be fast. So you will feel that okay, I'm going very fastly. So I will reach to my destination in a very short amount of time. But is it so? I hope you understand what I'm trying to say. So should we keep this alpha big or small? Small. Anyone? Small? Why? Small alpha will take a longer time to reach to my lowest point.
It should be, I guess, optimal.
not so big, not so small. If it is so small, then it will take lots of time to learn the things.
Okay.
And if
And
it
if
is
it
too
is big,
large,
if it is too large, then what will happen?
then maybe we might miss out the precise answer that was actually we were looking
Okay. So, thank you, ma'am. So the ma'am has already given the correct answer. So now you
for.
graphically, if you see here, so say my alpha is too big. So say alpha is 2 here, and say I started from this place. So I started from this place. The next jump is here. Next jump is here. My next jump will be say here, and then once I come here, the next time this it will make a back. It will take a backward movement, and it will again come here. Then again it will assume that okay, I am again increasing. Probably if not at this time, it may take another jump to this place, and then it will start again moving onto this direction. So from here we started, and then we came to this point, then to this point, and then to this point. My lowest point is probably here. So I should have stopped here, but I have never reached to this point because from here my direct jump was this place, as ma'am was trying to say. So we are basically, and now you can feel that we will make an oscillation. So from here we will come back to this, but still this is lesser than this. We'll assume that okay, we have some more things to explore, so we may go up to this, and then I can start making a jump in this whole area. So if you say, and if your algorithm is running for a longer time, so if you have say given 100 iteration, and finally when you stop, say your theta values were at this location, so you are far from the local minima, say the minima, sorry, you are far from the local minima. So you will stop somewhere. So say you have given 100 iterations, so at 100th iteration you stopped, and at that particular time your theta 0, theta 1 were initialized, which were representing this error. So you will get a max bigger error. So in next iteration you may get a lower error. So if you are lucky, you may reach here also. So you may stop here also, but that depends. But if you have small alpha, then how we are going to moving from this place to this place? So we'll be going very slowly. This one, and then if I have to oscillate also, my oscillation will be in this small area. So wherever and whenever you will stop, so basically you will be in a very close vicinity of that minimum point which we were targeting. But if this is very small, so if you say that okay sir, let us make it very small, say 0.000001, then very low. So I will be moving very slowly, and it will take a number of iterations to reach here. So and it will take a number of computations also, because each iteration means a computation also. So it will take a long time, long computation cycle to reach to this point. But in that case, you are you have a higher chance to reach to this minimum point which we are targeting. So people have also devised several idea where this alpha changes. So initially we start with a bigger alpha, and then as we move closer, so after certain iteration, or with every iteration, say the alpha is decreased by certain amount, so that when we are in this area, probably the alpha becomes very small, and that oscillation can be removed. So adaptive movement we can do, adaptive alpha we can do, so learning parameter we can do. So people have devised several proposal for that. So I hope that this how we are going to, so in case of given a linear regression, given a sample data, how we can go ahead to find out the parameters which will fit. And once these parameters are fit, so once we have decided this theta 0 and theta 1, so now we know given any x value we can find out the y value. So that's the linear regression part. Now from here I will move on to the logistic regression, which is a different case than a simple linear regression. And in a similar fashion, this linear regression can be adapted or can be enhanced to accommodate, say even in nonlinearity we can also use nonlinear functions. But seldom we use it. So more variables I have already explained. If we have more than one variables, so how we can do that? So we'll have more number of parameters. That's all. So is there any point to be discussed or anything? Any query from the participants? No. Then probably we should move on to the other topic. So this problem is basically a regression problem, a curve fitting problem, or continuous domain problem. So we had continuous variables to predict. House prices can be anything. It can be 2, 2.5, 2.3, 2.8, anything. So these are continuous variables. But in several examples or several problems in real life, we have some just two labels or more than 2-3 labels, some discrete values. So here I am starting my case with these two labels. Some examples we already know, like email. So given an email, we want to classify whether it is spam or non-spam. So online transactions, like credit card transactions or any bank transactions, so whether they are fraudulent or not. So given an image of a body part, we want to find out a tumor image, obviously. We want to find out whether this tumor is malignant or benign. Given a movie review, we want to find out say whether it's positive or negative, automatically by machine, obviously, not by human being. Similarly with review sentiments, so given a review for any hotel or any product on e-commerce website, we want to find out, the machine wants to find out whether it's positive review or negative review, and so on. So in this sort of cases, this y is between 0 and 1 only. So in earlier case, this y was unrestricted. So this y was basically from infinity to from minus infinity to plus infinity. But now if we restrict this y to take on only two values, 0 and 1, not between 0 and 1, only two values, 0 or 1. So y will be either 0 or 1. Here 0 represents the negative class and say 1 represents the positive class. If that is the case, then how we can go ahead? Can this linear regression solve this sort of cases? If not, what can be the issue, or why it will be difficult, why we should go for a new regression cases or logistic regression and so on. So say consider this figure. So we have say collected some images of tumors, and this axis represents the tumor size and this axis represent just variable. So it is 0 or it is 1. So if it is malignant, so no malignant, and say this is malignant. So this is my input. So input is this tumor size. So size of the tumor are given. So there are 3, say this is non, so 0 class, and 3 say 1 class. And now we want to predict, or we want to fit a say, curve for that. So if we want to fit a curve, this curve will be like this only. Am I right? We can have a curve like this also. Can we have a curve which will be parallel to x-axis for this case?
I guess when there is no change in y value. Because that
okay, so y value is the output, not the input. So the input, the straight line should depend on x only. So that's why it will be, it can be at different angle. So it can be at this angle, it can be at this angle, but somewhere it will be dependent on x only, because this axis x represents the input values. So it will be, it cannot be something like this independent of x. So if I write this, that means y equals to say 3 or 4 or 2 or y equals to 0.5, then we will represent a line like this, and then say sorry, x equals to something, then x is a fix, then that will not be a case. X has to be varied. So we cannot have a parallel line to x. So it will be something like this, and then we can make a say statement like this. If say since y is between 0 and 1 only, so if I say that if the output is whatever output, so my output will be say hx equals to say theta 0 plus theta 1 x, and I have tuned this theta 0 and theta 1, and now I say that once I give this x value, and if this output, if this hx value is in between say is greater than 0.5, then I will output my y as 1. And if this output value, so let me just, so say here, if I say that, okay, I have kept my theta to be 0.3 and say 0.1, say something like this. Even it can be smaller, -3 also, or it can be -3 plus 1. And say if I give my, this is my hx. So hx equals to, I have fitted like this. So this is my fitted model. Now if this x is say 1, then this value will be less than 0.5. And if that is the case, then that will be termed as a class 0, or y can be say put as 0. If it is say x is say 10 or say 15, something like that. Say if it is 10, then probably it will become say 0.7, which is greater than 0.05. In that case, we'll say that y equals to 1. So that's what we are trying to say here. So we'll put a class threshold that if h theta x equals to at 0.5, and if the h theta x is greater than 0, then y is 1. If it is less than that, then y is 0. So a simple linear regression, I mean to say, a simple linear regression can be used as a threshold classifier. Am I right? It can be done. But there are certain, what are the issues? So let us take this case. So if I added some more, samples, then this line will start tilting this one towards this. And in this case, you can now find out that even these tumors which were malignant are falling into one side of that line. Because as you will get more and more bigger size tumors, you will find that this relatively bigger, relatively say closer to smaller size tumors which were malignant will now fall into non-malignant or benign class of tumors. So that's the issue with this sort of linear regression. If we are trying to fit in a case of say 0-1 problem or say classification problem, because this will depend on the data size. So what we can do? So since we want that my output should be 0 or 1 only, no other output should be allowed. And this h theta x can be, but in general in say linear regression, this h theta x can be greater than or equals to 0 or even less equals to 0. So basically this range is -infinity to +infinity. Now we are saying, okay, let us restrict this h theta x, and this h theta x is say restricted in between 0 and 1. How to restrict that? One very simple case is using the logistic function or sigmoid function. A sigmoid function, so we are saying now that whatever parameters we had, let us define a function g. So instead of, so earlier we had something like this, so we were writing hx equals to say theta 0 plus theta 1 x. Now we are saying, okay, let us define this to be a function of some other some other function. This to be a function of, so hx is a function of some other function also. And this g, what this g will do, so the job of this g is to restrict whatever was coming from this one. So whatever is coming from this area, so g will restrict to that output in between say 0 and 1. So in between 0 and 1. So this g will be a continuous function, and which will restrict the output, or which will plot, or which will say enforce this output of theta 0 plus theta 1x, whatever value it may be, to fall in between 0 and 1. And one such function is sigmoid function, which is normally written as 1 by 1 plus e to the power minus z. So zz can be written as 1 by 1 plus e to the power minus z. So if we plot this function, I think I have a plotting, it looks something like this. So we have a sigmoid, a logistic function like this. And since we are using a logistic function, we call this regression to be a logistic regression. So this function is normally called as logistic function or sigmoid function popularly, and hence this name of this regression is logistic regression. So now if you see in this figure, so what this represents? So this also represents that this hx now represent the estimated probability that y equals to 1 on input x. So for example, if we say that h theta x equals to 0.7, that simply says that there is a 70% chance that the tumor is being malignant. So if we know, since it is a two-class problem, so if we know that one class is 70%, the other class can be computed by this formula. So it can be written as h theta x can be written as probability that y equals to 1 given x parameterized by theta, or equation in terms of equation we can write it as p of y equals to 0 given x and theta plus p of y equals to 1 given x and theta equals to 1. So p of y equals to 0, x and theta equals to 1 minus this. Or the chance of tumor being benign is 1 minus say 0.7, so it's 0.3. That's the other way of interpreting this values. So if I say that some value is falling here, say at 0.6, that means there is a 60% chance that that particular class is going to belong to say class 1. If say something is 0.4, that means there is a 4% chance that it will belong to class 1. That means there is a 0.6% chance that it will belong to class 0. Okay, so that's what this equation tells us. If you look into this equation, so we are saying that okay, at 0.5 we have a crossing. So since at 5 we have a crossing, that simply means that whatever value is coming, so if that is lesser than and at here it is 0. So this y-axis, the value of y coordinate is say the x coordinate is 0. So if I say that in this equation, when y equals to 1, this greater equals to 0.5, thus also implies that this value is greater than 0. So at greater equals to 0, or in other word, so this side is positive, this side is negative. So this side means what? This side means this value. So whatever was there before g, that should be greater equals to 0. And this value means whatever was there inside g, like, so this value, so theta 0 plus theta 1, in this case theta 0 plus theta 1 x, if it is greater equals to 0, and that's what is shown here. So if that is greater equals to 0, it is coming at this point. So at 0 it is coming here, and greater than 0 means on this side. So that's what is being told here, that if y equals to 1, when y equals to 1 only when this h theta x is greater equals to 0.5, and this implies that theta transpose x, or theta 1 of say theta 0, this theta transpose is a basically single notation for theta 0, theta 1 and so on. So theta 0 plus theta 1 x is greater equals to 0. If that's the case, let us consider one example. Say if we have a two variable case. So if we have a two variable case, then we know that in normal linear regression we can write it in this way: theta 0 plus theta 1 plus theta 2. So sorry, theta 0 plus theta 1 x1 plus theta 2 x2. I hope I am clear till now. Is it okay, this logistic part, what exactly is, why we are saying this term? Okay. So say if we have a linear regression, so everyone is very hungry now, it seems. So if we assume, I'm audible? I'm not getting any response.
Yes, sir, it's audible.
Okay. So thank you. So if we assume that this we have a case of two variables, so say theta x1 and x2. So if we have say a tumor size and color, say for example, then we can write a linear regression as theta 0 plus theta 1 x1 plus theta 2 x2. And if we put a z here, so that will z here means 1 by 1 plus this. So that will make it a logistic one. Now if we assume some say initial value, say theta 0 is minus 3, theta 1 is 1, theta 2 is 2. Then when this will predict 1, when this value will be greater equals to 0. So this whole thing, this hx will be greater equals to 0.5. This implies that whatever is this side on this inner part, this should be greater equals to 0. Because from this figure, I have told that if this is positive part, so here this line represents hx. So if this hx is greater than 0.5, this is 1. Hx is greater than 0.5 means what? What is inside G? That should be greater equals to 0 because this line is for 0. So that's what we are saying, that if that's the case, if we want to predict y equals to 1, that means this value. So this value we have taken initial value as minus 3, theta 1 is 1, theta 2 is 1, then minus 3 plus x1 plus x2 greater equals to 0, or we can say x1 plus x2 greater equals to 3. So the discriminant line, if these variables are diagrammatically represented, then this plane, so x1 plus x2 greater equals to 3, this plane will bifurcate, or this plane will differentiate the positive cases and the negative cases. And these cases can also be used for say non-linear example. Non-linear cases, we can use this, even this logistic regression can be used. So here we have an example of a non-linear say boundary. So we have certain samples, obviously this belongs to one class, and whatever is on the periphery, this belongs to the other class. And now say if we thought of, or if we presented this, we know that this is a non-linear surface, so we had a non-linear equation like theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 square. And let us take a random value, initial value, say theta 0 is minus 1, theta 1 is 0, theta 2 is 0, theta 3 is 1, theta 4 is 1. Then this will be 1 if minus 1 plus x square plus x2 square is greater equals to 0. That means this outer surface is basically minus 1 and this inner surface is 0. Sorry, this is 1 and this is 0. So that simply says that x1 plus x2 square is greater equals to 0. That now you can assume that this will be a circle. So you can find out, or you can draw a circle here, and that circle will now differentiate this. So inside this circle, if it is less than that, it will be 0. If it is greater than that, it will be 1. So that's how we can use even a simple linear this sort of equations. The non-linear surfaces can also be separated, or we can create that discriminant boundary through a logistic function. Now, what about the cost? That's the important question. Now, we talked about in earlier case, like even in this case also we can see that we have theta 1, theta 2, theta 3, theta 4, so many parameters. So 5 parameters are there. Now, how to find out the values of this parameter? So say if we use this same gradient descent technique, how this gradient descent technique will work. So if you plot this gradient descent, because this is a non-linear say equation, so as I was telling that if you plot it, since there is no time to give you one example of this, but I will request those who have they're willing to see the effect, they can take some example and try it. So now they can see that the error surface may look something like this. Since this is non-linear, so this G is 1 by 1 plus e to the power minus something, these values, minus of these values. So this error, if you go in a similar way of say hello. E square, if we go in a similar way of E square, it will become a concave area. So it will become an area something like this. And now we know that those who know hill climbing or gradient descent. So if you start from say this point, probably you may stuck at this location, or if you are very lucky, you may come to this one. But coming here or reaching this, say this is the lowest point, is now very difficult question. So very difficult thing to do. I'm not saying it is impossible, but obviously it is difficult than these cases, because here we had a straight area, a straight surface, so we are just coming down in this case. But here, once we'll come here, then you can find out that this is increasing, and then you will bounce back. You will thought, okay, this is my minimum, but in reality, this is not the minimum. And so, what else we can do? I hope I'm clear exactly what will occur with this error. So if you, any surface, even with a simple example, simple say linear cases, if you take, not only with this non-linear case, even with a simple linear case, if you try and find out this error may represent something like this, a surface like this. That simply means either you have to do some sort of, or you have to find out some new error function, which will more or less represent a cases like this, a convex case, or you can find out some robust algorithm, some sort of say genetic or that sort of particle swarm optimization sort of thing, from where you can find out the local minima. So these two options we have. So instead of going into that say bigger meta-heuristic techniques, let us think of how we can modify this error functions, which we had earlier defined to be y minus y hat whole square, so a squared error. How we can change this error function, and we can define a new error function which can basically take care of this issue and can give us something like this. So if something like this is obtained, our life will become, or anyone, these algorithms life will become very easier, because this can easily find out, or it is relatively easier, quite easier to find out this minima compared to this. So what we can do, or how to do that? So we define an error function like this. So we define an error function, cost of or minus of log 1 minus h theta x. Oh, sorry, this I should be x. It should be removed. There should be, sorry, this I is if y. So due to this is a misprinting. So if y equals to 0, now how this looks like. So let us see this. See this one. So let me write up this. Let me draw this. So what we are trying to do is, we are trying to find out, so my cost is, my cost, say j theta is minus of log, and this is h x, obviously theta. So this is what we have, and say this h theta will give us some value. So say z. Now if you plot log of z, how it will look like? Log of z, only log of z. So if it is say 0, it is say 1, in between 0 and 1, how it will look. So log of 1 means 0, and as we go down, it will decrease something like this. Am I clear? So this is 1 and this is 0. Log of 1 is 0, and as we go down, it will start going down and down and down, and asymptote at 0. So this is how. If we take negative, then this will, if we take the negative case, then this will look something like this. So just it will start with this one, and at 1 it will come to be 0. And the other case is minus of log 1 minus z. So this case will be just reverse of this. So at z equals to 1, so this is 0 and this is 1. So at 1 it will become 0, and at 0 it will be 1. So at 0 it will be 1, and hence this line will move like this. So this is a case for this, and this is the case for this. Now if you combine these two, so if you combine these two, you will get something like this. And in fact, these equations can also be, you can see here I have written it in 2 lines. This can be written in single line also. I hope this figure is clear. I hope you have become hungry. So there is no response. We can write it in this way: minus y log of, say, h x minus 1 minus y log of 1 minus h theta x. So this is what is written here. So minus log x theta x if y is 1. So if y is 1, we can multiply this y here. So that's what I have done. Minus y into log of h theta x. And this is log of 1 minus h theta x. Since y is 0, so 1 minus y will be 1. So that's why we are multiplying 1 minus y here. So if I write 1 minus y log of this. So these two now can be represented by this equation. And now you can see that this is basically a convex surface now. So if we start either from this point or from this point, we have to find out this minima. We have a fixed minima, and we are trying to come to that fixed minima. This error function is known as, can anyone name this? I think all of you know. This is binary cross entropy loss. This is cross entropy loss. So this cost is 0 if y is 1 and h theta x is 1. So if both are same, the cost is 0. But if h theta x is 0 and y is 1, then this cost will tends to be infinity. So we are saying that we will penalize this algorithm if it is wrong. So that's what is shown here. So if y is 1 and the output is also 1, the loss is 0. Otherwise, there is a huge loss. Similarly, if y is 0 and the output is also 0, then the loss is 0. So this will be 0. Otherwise, there is a huge loss. So these are the figures we have already drawn. So this is a single equation where this loss can be represented. So in a non-linear decision boundary. So this is even for any cases, whether it is linear or non-linear, we can represent it like this. So with that, today I will stop because it's already 1:30 and I cannot get any response. So I assume that you are now too hungry. So because you have a session from 10 o'clock, some question or some clarification, some suggestion.
So participant, if you have any question, please you may directly ask to J.P.Singh sir.
Sir, this is Sneha.
Yes.
Will you be posting the material, sharing this?
Yes, sure. All these things I will share it with Madam Ranjita Madam, and probably she will post to the candidates. Obviously, she might have made certain plans to share these materials.
Thank you, sir.
Yes, I'll be sharing with you once I get it from the expert speaker. I'll be sharing. Okay. Thank you, ma'am. Thank you so much, sir.
So if there is no query from the participant side, let's close this session here. We'll meet at 3 p.m. for the last session of this. Okay, thank you, sir, for your insightful session. I hope all participants has enjoyed your session.
Thank you, ma'am. Thank you, everyone, and see you tomorrow.
Thank you, sir.